Okay, in this unit, we're going to do machine translation and attention. And so first, let's talk about the problem of machine translation. So in machine translation, we have an input sequence of words in, say, German, and we want an output sequence of words in, say, English. So the translation problem is a sequence-to-sequence problem. And the paper I'm going to be talking about is sequence-to-sequence learning. This is a paper that appeared in NeurIPS in 2014. And this paper really shocked a lot of people. I mean, it's a long time ago now. But this is the paper I mentioned earlier. Ilya Sutskever gave the talk, and he made this statement, which really had an impact on me, of having maximal effect with minimal innovation. So the idea here is, at least often stated, I think of it as part of the dogma of deep learning, is that you can do something quite naive with a neural network, and the neural network will learn to solve your problem. SGD over a lot of parameters is magic, is the idea. Okay, I want to point out as we start that this sequence-to-sequence problem is approached using an instance of our fundamental equation. So we're going to define a probability distribution. The model is going to have parameters phi, and it's going to define a probability distribution over the output translation of an input sequence. And the output translation can be of a different length than the input sentence. But the training objective, the loss that we use in SGD, is simply minimizing the expectation over the population. Now, in this example, the population is just a big corpus of translation pairs. So we've got, in this paper, it was English-French. So we've got a bunch of pairs of English and the French translation. And we want to just minimize the minus log probability of the English translation given the French. I think that's the direction I used. So of the output given the input. So that's just our standard fundamental equation, minimizing over the parameters, the average over our XY training data of minus log the probability of the output given the input. And we talked about the structured case. This is the structured case where the space of possible outputs is way too large to consider looping over all possible output sentences. So in that case, we're going to have to use an autoregressive model. We're going to have to predict one word at a time and compute the probability distribution over the next word as we go. So this is the approach this paper took. It's going to take the input sentence, and it's going to run an RNN, a recurrent neural network, over the input sentence to get a final vector. The final vector of the RNN run over the input sentence is going to be a representation of the input, but it's a vector. So people call that a thought vector. It's the vector representation of the thought being expressed by this sentence. That's another strange sort of concept, a thought vector. It's gotten more comfortable over time, but at the beginning of the deep revolution, this was quite a mind bender. But the thought vector in translation, English to French translation, the thought vector for the input is going to be computed backwards. So it's going to be computed from the end of the sentence forward. I should say I'm being a little fast and loose. I'm presenting something that's very close to the paper that was presented, but that's simpler and conceptually easier. So conceptually, they did something equivalent to this, but in my version, I'm going backward over the input. If you go backward over the input, that means that your thought vector, the most recent word it saw, was at the beginning of the input. And then we're going to take that thought vector and we're going to do an autoregressive language model conditioned on the thought vector of the input. So we're going to take the thought vector of the input as the initial state of a forward RNN that generates, in the sense of a language model, that generates one word at a time by probabilities, generates the output sentence. So this is very simple, very naive. And I remember it was shocking that this worked at all. It was not state of the art at this time. Neural methods became state of the art in machine translation shortly, but it was shocking that you could just represent the input with a vector, then do a conditional language model from that vector, and it worked reasonably. There are people whose legacy is a quote, and I can't help but tell the story. So a typical example of this is Eugene Wegner. His legacy almost is the title of a paper he wrote on the unreasonable effectiveness of mathematics in the physical sciences. Everybody knows that quote. Fred Jelinek was a speech recognition researcher, and his legacy almost is the quote, every time I fire a linguist, our recognition rate improves. Sort of a saying that linguistic theory was not doing much for his speech recognition systems. So Ray Mooney at University of Texas, Austin, looked like for a while he was going to have a quote legacy. The quote was, "You can't cram the meaning of a whole bleeping sentence into a single bleeping vector." And that quote got a lot of repetition. A lot of people were quoting that, and now people are starting to believe it, that you can cram the meaning of a whole sentence into a vector. But anyway, that's an interesting story. I was very sympathetic to that idea that this was a very strange thing to do. Okay, so how's this going to work? I'm going to have a few slides here on the problem of machine translation. So I just told you how we train this machine translation system at a very high level. It's very simple, right? We take the input, we run an RNN, we get a thought vector, we take that as the initial vector of an autoregressive language model to get the output. Very simple. Minimal innovation for maximal effect. In the paper, it was the RNN was actually 4 layers deep. We talked about layering RNNs. So it wasn't quite as trivial as I'm saying, but that layering is also a very simple standard thing. But I'm just going to make a few observations about the machine translation problem. So when we go to actually do translation, we've got an input sentence, we have to do translation, we have to pick an output sentence. The model is defining a probability distribution over the output sequence given the input sequence. So one thing we can do is sample from that model. It's a language model, an autoregressive language model. Autoregressive language models you can sample from them. You can sample the next word as you're generating words. And you could take a sample to be the translation. You can also do a greedy decoding. There's this idea that the most likely, you don't really want just a random sample, you want the most likely translation. That's probably going to give you the best blue score with the way these things are evaluated. So in practice, what people do is instead of sampling from the distribution to take every next word, they take the most likely word one by one as they go. And that's greedy decoding. And you can also imagine trying to maximize the probability of your final output sentence. So try to do something to maximize the autoregressive probability of the whole sequence of the output. And this is not the same. These last two things are not the same. Greedy selection of the next word does not guarantee that you've got the maximum word sequence in the end. And here's just a simple example. Let me just jump to a simple example of that and then I'll go back. So consider those apples are good versus apples are good. Now it's perfectly plausible that the most likely first word, that the word those is more likely than the word apples as a first sentence. But if I pick apples as the first sentence, I can make a complete sentence more quickly, shorter. And shorter sentences have higher probability. So this is just an example of where the greedy choice can produce a sentence of lower probability than something that can sort of look ahead and look into the future and see how that choice is going to affect words downstream. So a typical way of addressing this issue of picking words that work out well downstream is beam search. So in beam search, we're assuming we would like to find a word sequence. So I'm using a capital letter here to indicate a whole sequence. And I want an output sequence that is the argmax sequence of the probability of the output sequence given the input sequence. In beam search, at each time step, we maintain some list of choices so far. Each choice so far is a particular sequence up to that point in time. And then when we pick the next time step, we pick a bunch of options for each one and prune it down to K. So at each point, we have a K best list, and that's beam search. So I just wanted to make a few comments about the machine translation problem. I mean, I could also go into scoring it and blue score and so on, but I'm not going to do that. Machine translation with attention. This is another paper that appeared a week earlier. But the Sutskever paper appeared at NeurIPS, and this paper appeared at iClear, and NeurIPS was maybe 3 months, 4 months sooner than iClear. So by citation count, that earlier sequence, the sequence paper got a lot more citations, and it shocked a lot of people. Somehow it got press earlier. This paper is much more sophisticated, works better, this paper we're going to do now. And I always felt it was a little unfair. I mean, I don't know if arXiv really should count as precedence, but it did appear on arXiv a week earlier. All right, so again, I'm going to describe a simplification of this paper. This paper introduced, this is the first paper to introduce attention. Attention is incredibly important in modern architectures, and we're going to see that in the next unit. We're going to see where attention went after this paper. So the first thing we're going to do in this paper is we're going to replace the thought vector. So this is what we had in the Sutskever paper, where we have a conditional language model that's generating, it's an autoregressive model, it's generating one word at a time, but it's conditioned on the thought vector of the input. That's one vector. Here, what we're going to do is we're going to run a bidirectional RNN over the input. And instead of picking the one endpoint as the representation of the input, we're going to take that whole sequence. So remember that a bidirectional RNN is computing hidden vectors left to right and hidden vectors right to left. And then for any point in time in the middle of that sequence, I can take the two vectors, one coming left to right and one coming right to left, and concatenate them and get a vector for that point that has both of those. So I'm going to write that vector, the bidirectional RNN, with this bidirectional arrow. So this is a sequence of vectors. So it's a matrix. It's for each time we've got a vector. If I write a little t, then we're talking about the vector at time t. So now we're again going to define an autoregressive model, but instead of being conditioned on a single thought vector, it's going to be conditioned on this sequence of vectors. And that's going to give us more information. You could play with the dimensions to try to make it the same information, but that sequence is going to give us, the architecture is going to work better by working out alignments in time between the input and output. The title of this paper involved alignment. So now what we're going to do, the idea behind attention, is as we're generating words, autoregressive in the output, one word at a time, we're going to try to figure out where in the input our translation is coming from. So the intuition is when you translate English to French or French to English, there's an alignment. Each word or phrase in the input is appearing at some place in the output. And we want to get that alignment into the algorithm, into the architecture. We want the architecture to be able to represent the alignment between where you are in the input and where you are in the output. And that was the origin of the attention mechanism. Okay. I like equations more than I like pictures. It's just the way I am. So this looks like a terrible slide. Lots of equations, but it really has three parts, two of which we've gone over already pretty carefully. So the first two lines are just the definition of autoregression. So the first two lines says we're going to generate an output word one at a time, conditioned on the representation of the input, which is now this sequence of vectors over the input, and the previous words that we've generated in the output. So the probability over the next word is looking at the input and the previous words. And that probability is just a softmax of over the words, because it's the probability of the word, so it's a softmax over the words of the vector representation of that word, inner product, a state that's produced by a kind of RNN that's run over the words so far. Okay, so that's exactly what happened in the earlier paper, in the Sutskever paper, right? Is you have a representation of the input, you construct an RNN that's running over the word so far. To get the probability distribution over the next word, you take a softmax to get a distribution of an inner product of that word's vector and some state that's computed as you go along. Same, so this is the same as it was for the Sutskever paper. Okay, what's the RNN that runs over these words? That's where the difference is going to come in, because that RNN that's going to run over these words can look at this whole sequence. So this RNN, we initialize the hidden state of the RNN. We're going to run an RNN over these words. We initialize its hidden state to be a kind of thought vector. So we're going to take the concatenation of the two final RNNs, two final RNN states, the one going left to right, we take the right hidden state, the one going right to left, we take the left hidden state, we concatenate those, and we get a thought vector. That thought vector is just the initial state that we're going to use when we start generating this. But then as we generate things, we have to update the RNN state, the hidden RNN state, because that's going to be used to generate the next word. And that's just an RNN cell. But the normal RNN cell has two inputs, right? It has the previous hidden state and the next word vector. So from the previous hidden state and the next word vector, you get the next hidden state, if that's a picture, okay? However, when we're doing translation with attention, we have a third input to the RNN cell, this vector. And this vector is representing a direct access to the input, okay? And that so there's a direct access to the input here. And how does that access to the input work? That's the new part of this paper. So that's the attention mechanism. So our input is this bidirectional sequence of vectors. I'm thinking of this matrix as a sequence of vectors. And what I'm going to do is I'm going to construct a probability distribution over time and take a weighted combination of this as weighted by this weighting according to time. And so what's happening here is we're taking a sum over time, over the input time. I'm using capital letters, that's giving a sum. The sum over the input time is the sum of the input time. This is a convex weighting over the input time, a probability distribution. And for each input time, we've got a vector. So if this was focused on one point, we would be getting one particular place in the input to be this vector that's input here. If this is focused on one point, we pick out a place in the input and put it there and put that and feed that to our cell. Okay, so how is this probability distribution over the input computed? Well, probability distributions are computed with softmax. So this thing is a softmax over the Tn. So it's going to be a softmax over the input positions of the word vector that you just generated. So we get to look at the word vector. We're computing the next hidden state. So we get to look at the word vector we just generated. So we're going to take the word vector we just generated and take an inner product between that and all the positions in the input state. And then we're going to take a softmax over that, and that softmax should be giving us positions in the input state selected by the word that we just generated. So you can think of that as a kind of alignment between the input and output. So this is a kind of alignment between the input and output. It's saying at output time t, there's a word that's being output at time t. That word that we're outputting at time t selects where we are in the input. Once we know where we are in the input, we take the hidden vectors at that place in the input. It's soft, so it's a weighting over the input, and we're taking a weighted sum over the input. And that feeds the cell of the RNN. Okay, so it's a little involved, but I hope I unpacked these equations sufficiently. Let's look at just the attention part again. The attention part is what's new, right? So we've got this sequence of vectors, and you can really think of this as some arbitrary sequence. This mechanism is going to work for any arbitrary sequence or maybe even set of vectors. And what we're going to do is we're going to take some query vector and we're going to compute a softmax over the positions in this sequence as to how well they match this query vector. And that's going to give us, this softmax is going to give us a probability distribution, a convex combination over this T in for this T out. And then I can take that convex combination and use it to select or to weight the elements of this vector by their weight as defined by this attention. This matrix is typically called the attention matrix, but typically an attention matrix is always used to extract information from the thing that it's an attention over. So this is a very general mechanism for selecting parts of a sequence of vectors. And this has really become ubiquitous in deep neural networks. Attention now is all over the place. Let's consider, so this was 2015. Actually 2014. Very quickly, by 2015, attention had been applied to image captioning. So you can think of image captioning as a kind of translation problem. I give you an image, you generate a caption. So the image, it's image to sequence. But you can think of that image as just another abstract input. And the way you apply an attention-based translation from image to caption is you construct a set of vectors at all the positions in the image. And that's like the vectors constructed at the position of the input sentence. And then as you're generating your caption, one word at a time, each time you generate a word, there's an attention over where in the input that word is aligned, right? So in language translation, you're aligning the output to the input. Now we're going to do image to caption translation. We're aligning the words in the image to positions, the words in the caption to positions in the image. And so here's some examples. So this is ICML 2015, really quick. So as we're generating the caption, a woman is throwing a frisbee in a park. I can stop and ask, where does the word frisbee, what attention do I get when I do a query on the word frisbee into the image? There's a vector at each place in a fairly coarse grid over this image. And you can see the frisbee lighting up. A little girl, so now we compute attention based on the word girl, sitting on a bed with a teddy bear. And you can see that the word girl is lighting up this place in the image with the attention. And the next unit, we're going to talk about the transformer. And the transformer is attention on steroids and has completely replaced RNNs. So next time. Thank you.